And we are back. And so we are going to talk about isomeric states and specifically the difference between isomers and conformers. So there are quite a few isomeric states, and we are going to actually talk about all of these different isomeric states. But first, we have to understand what are isomers. So isomers or isomeric states are molecules which are compositionally identical. So same composition of atoms, but they are structurally distinct. And this is the key phrase here. They must be structurally distinct. Now, conformers, on the other hand, they're also, again, compositionally identical, but they can be related by rotations around a single bond. So what does that mean, actually? So let's say I have a molecule that looks like this. Let's say I have H, and let's say I have, for example, Cl, H, and then, for example, I've got C, H, and then you can have Cl here, H, and then you can have ClH. So these two are compositionally identical, but you see that we've rotated basically around this single bond here to change the positions of our CLs. Now, these, again, they are conformers. They are compositionally identical, but they are not structurally distinct because atoms can rotate 10 to the 24 times. They're always, especially around single bonds, they are mobile. They are moving. They are rotating and vibrating. So they go through these rotational states, but these are not isomeric states. So they can rotate essentially around these bonds. So this is not an isomer. This is a conformer. Now, once you have a double bond, especially this double bond along the backbone of the carbon, a double bond, or even worse, a triple bond, there are no more thermal rotations. They are effectively, it's zero. So if we look at this molecule here, and you can hopefully maybe remember this from chemistry, here, I mean, this is also a structural isomer. They are, again, these are, actually, this is actually a structural isomer because you can see here, you have atoms here, so you can't just like flip these on the side here. But even if this was, kind of, let's say we wrote another one that looked like this. For example, let's do H and let's do Cl, and then let's keep this as H and then Cl. These are not isomers either, again, because you can't just rotate, around that double bond. So these would be rotational isomers, or actually a variation of them. Or actually, these would be geometric isomers. Actually, you can tell this would be, actually, these are also, this is a subset. So this is cis isomers. This is a trans isomer, isomeric state. But again, we can't rotate around that double bond in order to, again, find, you're not able to rotate around that carbon bond, that double carbon bond. And so you cannot essentially recover that original structure. So these are isomers. So, and actually specifically, this is a cis isomer and this is a trans isomer. So these are versions of a geometric isomer. A structural isomer as well, actually these are also structural isomers. It's a version of, a structural isomer would be something like this, where you have, let's do 3. And I know this is going to take, I'm just going to cheat a little bit. I'm going to do this as H2, and then H, and then, I don't know why I just didn't do CH3, but anyways. Let's do H, and let's just put like F here. And then let's say we have another molecule that looks like this, where it's like C, like F, H, C, H dash C. Let's make sure we're still good. Yeah. H2. I believe we're okay. Yeah. So this would be an example of a structural isomer. Now we can also have, again, you can also have now a really cool class of isomers. A sequence isomer is really about, like, so if you have a block copolymer, so like block A, block A, block A, block B, block B, block B. And then if you have a block of polymer that's arranged like this is just a random block of polymer, these would be sequence isomers. So again, chemically identical, 3A's, 3B's, 1, 2, 3A's, 1, 2, 3B's. So these are chemically identical but structurally distinct. So that is what the that's essentially the difference here. So you can also have stereoisomers. So stereoisomers come in these kind of three distinct forms. So if you have polymers, lots of times polymers can have these kind of hanging like side chains. And the arrangement of the side chains, and this is the origin of these kind of side chains that kind of grow out. This is the backbone structure of a polymer. And the origin of these side chains really depends on the type of polymerization. It's actually chain polymerization rather than sequence polymerization. But that is kind of the key aspect here. So these are different, again, chemically identical, but the arrangement of these side chains, actually it's radical chain polymerization. You can look at some of my videos on the polymers playlist to look at that. But the arrangement of these side chains, again, chemically identical, same number of side chains, but if they're arranged on one side, we call that isotactic. If there's kind of this repeated pattern, so it could be like 1, 1, it could be 2, 2. If there's some repeating pattern, we call that semiotactic. And then if it's completely random, atactic. Now, again, why are we talking about these isomeric states? Like, what's the point, Professor Steimel, of this discussion? There's actually a great example. So there is one of the classes that's not shown here. We talked about geometric isomers, but you could also have basically optical isomers. So basically, you could kind of imagine, like, if you draw your hand, like a left hand and a right hand version. So in the, I believe it's 1950s, there was a drug, thalidomide. Thalidomide comes in two isomeric forms, a left-handed version and a right-handed version. One version, I can't remember which, and actually I'm going to look it up this time. Which is, let me look just quickly, which one was it? I believe it was the which one was it? Let's see, isomer. I believe it was probably I think it was the S isomer version. Yeah, the S isomer version was the one that had the birth defects involved. So, excuse me for that. I just went off on a tangent. But so this drug, thalidomide, was prescribed to basically reduce the impact of morning sickness in pregnant people that were pregnant. But the problem is one drug is very effective at reducing morning sickness. One drug caused really horrific birth defects. And unfortunately, in the 1950s, a lot of people were prescribed the other isomeric form. So again, in this course and moving forward, especially into lecture 2, we are really going to emphasize that, again, structure dictates properties. And this simple flip, which again, oftentimes, when you're looking at these isomeric states, it looks so, what's really the difference between the two? But these structures have significant impact on properties and can sometimes have devastating effects. So we really have to be cognizant of these, structural changes and how they can impact properties. And so speaking of properties, these are all polymeric forms. And oftentimes, polyethylene is produced from chain polymerization. And oftentimes they create these branches that impact whether it's low density or high density polyethylene. And if you look at how can we stack or how can we arrange these structures, if I have an isotactic form, I can stack these interactions really, really, really close together. And my intermolecular interactions, my van der Waals interactions, my H bonds, those bonds, the strength, I think the force of those bonds decay is like 1 over d to the minus 5, the distance between them. So the closer that I can stack them together and arrange them, the more impactful, the stronger those bonds are, to remove them. And so if I have an isotactic polymer where I can stack and push those close together because of there's nothing pushing each other apart, your melting temperature is going to increase, your Young's modulus is going to increase significantly compared to syneotactic, because again, I can't stack, I'll have something like this that touches, and it's even worse for atactic. So we really want to be aware of, again, how these isomeric forms can impact properties. And finally, there's also this kind of subcategory of what we call rotational isomeric states. So you can kind of see with this molecule here, low energy state is the most probable. One of the cool things is you can always take an energy landscape and you can just flip it. So like the lowest energy is the most probable, highest energy is the least probable. So you can see it would just like be flipped like this. So why is this the lowest energy state here? As we rotate around this kind of single bond. So we can kind of see in this structure we have C, and then we have basically a CH3, and then we have an H, and then one more H, and then an H, and a CH3. So when my CH3s are the farthest apart, this is basically in the trans configuration, I'm at the lowest energy state here. If they're on the same side, kind of like it's shown here, I'm in the cis configuration, that's the highest energy state, that is not favorable. But you'll also kind of see, and here, again, this is another high energy state. Why is that? Well, because like these bulky molecules are near a hydrogen, they're close by. But you could also have these kind of local minimum states. We call these the Gauss plus and Gauss minus. And you see, they're not like overlapping. They're not kind of eclipsing each other here. So that's kind of why you see these. But this is a Gauss plus, Gauss minus configuration. So those are some things that you probably haven't heard before. But you can kind of see those. And you can see, again, how fast, 10 to the 10 times per second, they can change these configurations. So it's unbelievable. Again, things are moving. We're not just static. Materials are always, fascinating. So congratulations on finishing lecture 1. I wish you the best of luck on the problem set. Here's the bad news. There's nothing on your exam 1 that's probably going to be covered in lecture 1. But it's critical foundational work. And then we're going to hit it and get started in lecture 2. So we'll see you then. Thanks. Bye.